I just kind of realized that Thursday I spent some time, yeah, it was Thursday, getting some videos ready for this class on Tuesday. Anyway, and so now, um, uh, so I don't know why I'm hurrying, because I'm sitting here on a Monday afternoon thinking, oh God, I got to get this stuff done for you for tomorrow. I've already given you stuff for Tuesday. All right, this will be for Thursday. So anyway, so we're moving right along. But let's take a look at this. All right, and I'm going to add these problems, and they'll be blank so that you can print them off and look at them while we're going through. I'm going to try and get through 1 and 2, this one and this one in this video, and then we'll calculate this problem. Then we'll be done. I'll be done for the day, and then we'll look at some of the trickier problems that we have. That then you can use those ideas to help you with your homework and the problems I gave you. All right. So it says express the acceleration of any object down a frictionless incline. Okay. All right. So here's what we do. So first of all, we need a cleaner sheet of paper. We need a whole sheet of paper to do this, believe it or not. I mean, this is, all right, so here's what we do. We've got an object on an incline. And this is Physics 101 at its best. You cannot do Physics 101. You cannot say you took a Physics 101 class unless you do an Atwood's machine and have an object on an incline. Okay, we're going to assume the friction is equal to 0 here. So what's going to happen when I put this object on an incline? If there's no friction, it's going to slide down. And it's actually going to increase its speed because it's going to slide down, and gravity is going to pull it down. The only force that's pulling that down is gravity. So you might be saying, well, what's the force that's parallel to it? So let's look at the forces that are acting on it. First of all, we've got a normal force. Here's the normal force that's perpendicular to the force here, to the mass, or to the perpendicular to the incline. There's the normal force. And then we've got the gravitational force, which I'm putting those two vectors right here together. All right, because that's the beauty of vectors. Now, these two vectors are not the same. Because if I had this thing on an incline like this, the normal force would equal 0. Right? There is no normal force. The only thing that's going to pull this thing down is mg. It's going to free fall. We've gone into free fall at this point. So as I raise this, as I make this angle bigger and bigger, the normal force gets smaller and smaller until this is in free fall. So we're going to look at it like this. All right? Now, here's what we're going to do. We're going to rotate this thing like this. We're going to rotate this thing until I got the normal force going straight up, okay, in the y direction. I've got an x direction going this way. All right, and look what happened to gravity. It's now cattywampus. So instead of rotating my paper, we're just going to, that's what I'm going to do. I'm going to make the normal force now go up, straight up. I'm going to turn the block into just a box like this. And now we saw that mg, which is the only other force, is actually going this way. I've noticed that the OpenStax book tried to do this a little bit differently, and it's fine the way it works. I've got a cattywampus vector. I've got a regular vector, and I have a cattywampus vector. Okay? I'm trying to figure out the acceleration on this thing. What do I do with a cattywampus vector? A vector that's at an angle. That's right. I break it down into its two components. It's got a y component going this way, and it's got an x component going that way. So this is m1 g. Now notice, the x component, though, here's the angle theta. Due to some basic geometry, this angle is equal to this angle. Okay? We could go through the geometric proof of it, but we don't need to. All right? So I've got an mgx. But notice, x this time is the opposite leg, an mgy. Okay? mgy is equal to m1g1, m1g times the cosine of the angle. mgx is equal to mg, m1g, times the sine of the angle. What? You mean you got something that's in the y direction is a cosine? Yes, because remember, cosine don't care if it's x or y. It just cares that it's the adjacent leg to the hypotenuse. And that's what we have. Well, now we break it into two parts. We break this into two parts. And we come up with, we've got, okay, I've got the sum of the forces in the y direction are equal to the m1 times some acceleration. Okay, now, in the y direction, is this block flying off this way? Is it crashing through the incline? No. So in the my in the y direction, so the acceleration in the y direction is equal to 0. It has no acceleration in the y direction. This is equal to 0, so I got a normal force minus m1g cosine of the angle. All right? Now, we're breaking into the x and y components. So now the sum of the forces in the y direction is equal to m1 times ax times the acceleration in the x direction. And this definitely has an acceleration vector in the x direction. Is there anything else operating on the block? In other words, I can bring this vector up here like this. No, there is not. So that is equal to m1 times g times the sine of theta. Okay? So without friction, the gravitational force that pulls something on an incline is always equal to m1 g times the sine of theta. So, according to our problem here, express the acceleration of an object down a frictionless plane that makes an angle theta with the horizontal. Assume down is positive. Okay? So, here we go. What do we have here? Here's the expression for it right here. Well, to get the expression for it, I divide both sides by m1. So the acceleration in the x direction is equal to g sine theta. Now we'll look at it with friction.